Hello everyone, I'm Daishan Li, a first-year PhD student from UIUC. Today, I'm very glad to present UniHeap, managing persistent objects across managed runtimes for non-volatile memory. This work is in collaboration with Ben, Jinghan, Tom, Professor Joseph Torellas, and my advisor, Professor Jian Huang. Nowadays, non-volatile memory has become a promising technology. It offers near-DRAM speed, scalable memory capacity, wide-addressable interface, and data durability. However, the biggest challenge is that programmability of non-volatile memory is still a problem which hinders the widespread adoption of a non-volatile memory. Why is this the case? It is because in modern memory hierarchy, many levels of volatile cache exist between non-volatile memory and the processor. For example, the processor cache and DRAM. In this case, the order of an object update to be persistent is dependent on when it is evicted from the volatile cache. In order to ensure the persistent order, we need explicit instructions, for example, cell BB and sfns in x86 processor, to explicitly flush the cache line to the non-volatile memory and make sure it completes. We also need to mark all the persistent updates in the code to track each object update that needs to be persistent. This must be done very carefully because if we miss a single one, there will be correctness problem because we do not persist all the target updates. If we have redundant instructions, there will be performance bugs because we suffer from redundant flush. So programmability of non-volatile memory is still the biggest challenge you can see. To address the programmability issue, we can leverage managed runtime to manage non-volatile memory. There are mainly for two reasons. First, managed runtime can transparently manage hardware complexity and data objects. For example, in Python, programmers do not need to manage object lifetime or to manage memory addresses in the code. This property makes it practical for the managed runtime solution to provide easier to use persistent API for non-volatile memory. Another reason is that managed runtime is broadly used in many popular programming languages such as Java, Python, and JavaScript. So managing non-volatile memory with managed runtime could become a pervasive solution. Along this path, we have already had some initial efforts. Our previous work, AutoPersist, published in PLDI 2019, is an easy-to-use framework to manage persistent objects on non-volatile memory. Instead of marking all the persistent objects updates and adding persistent instructions, AutoPersist only requires developers to mark the durable root objects with a simple annotation, as shown in this figure. Then the managed runtime will automatically and transparently persist all the reachable objects from the durable roots. Comparing to the previous work that need to mark all the persistent objects, AutoPersist achieved 16 times less persistency markings in the program, which significantly improved the programmability. So with AutoPersist, we can create a crash-consistent application much more easier. Note that everything seems good. So with AutoPersist, we can persist objects into non-volatile memory easily. However, AutoPersist can only support Java language. How can we extend this to multiple runtime, for example, Java, JavaScript, and Python? Because non-volatile memory is a storage device and is a system-wide shared entity, of course, we need data sharing among different runtimes. If we think about how traditionally storage devices do data sharing, which is file system, so file system enable data sharing across different programs with a file abstraction. So our runtime managed non-volatile memory framework is also naturally desired to enable the data sharing with a persistent object abstraction. In this case, we consider our managed runtime as a new file system for non-volatile memory. So with this property, objects created by one managed runtime can be easily accessed by another one. Let me give you 3 real-world scenarios to further elaborate why we need to support data sharing among multiple runtimes. In web services, a Java server can persist its objects in non-volatile memory and allow other programs written in different languages, such as Python, to access these objects directly. In shared library scenario, multiple Java or Python programs that are using the same library can concurrently access shared persistent objects together. In data analytics scenario, programs that are written in different languages can concurrently analyze the same dataset and create shared persistent objects in the analysis. In these scenarios, we see that object sharing among managed runtime are needed. State-of-the-art object sharing framework mainly fall into two kinds. One of them, Swift and Protobuf, are cross-language remote procedure call protocols, which requires serialization and deserialization of objects when it generates template codes. This will bring significant overhead. The other solution is memory sharing. It enables shared memory across many runtime, but it does not support non-volatile memory yet, and it also does not provide persistent object optimization for non-volatile memory. So to fill the gap, we present UniHeap, a new non-volatile memory framework for managing persistent objects to enable efficient object sharing on non-volatile memory. We propose a unified persistent layer that has a unified object model that can be extended for various managed languages. It also optimizes the object layout to reduce the persistent overhead. We manage non-volatile memory with a shared NVMe heap that enables cross-language object sharing. Achieving this is not easy. There are three challenges we need to overcome. Firstly, because different runtime have different object abstraction, we need a unified object model and type system for object sharing. Secondly, we need an efficient implementation that should ensure both persistency and crash safety with low overhead. Thirdly, because many runtime need to manage the data objects for the user. So when data objects are no longer in use, we need to do garbage collection for the user. Considering different runtime have different GC policies, we need to build an efficient and correct coordinate GC. First, let's look at the unified object model and type system. Because different runtime have their own object model and type system, to enable the object sharing among them, we build a unified object model and type system. We achieve this goal by providing two built-in types, numerical type and reference type. As shown in this table, the numerical type covers the commonly used types such as char, short, int, etc. For the reference type, the object field stores the pointer to a user-specific persistent objects. Our design principle for reference type is that it can support multiple container types in different managed runtime easily. So developers can implement their own reference type for different managed runtime based on the given numerical types. So based on this design, different managed runtime can then map their type to the test system of UniHeap as shown in this table. So for example, dictionary in Python is not treated as an object in UniHeap. So a reference type objects can be created with the object field storing a pointer to the dictionary. As we have finished the unified object model, now let's look at how we ensure the persistent and crash safety implementation in UniHeap. We first show how object persistency is enabled in UniHeap. So to be compatible with the automatic data persistence approaches in existing non-volatile memory frameworks, UniHeap gives two easy-to-use APIs. The first API, we can set durable roots and atomic persistent all the reachable objects. So in this figure, when R is set as a durable root, AB, which is reachable, will be put into non-volatile memory. The second API, programmers can use the interface atomic begin and atomic end to specify a failure atomic region that provide crash safety for all the durable objects in it and also provide an all or nothing visibility outside the atomic region. We now look at how to have an efficient implementation of the persistent object sharing. So the traditional way of ensuring persistency is use undo and redo logs. Undo and redo logs write the log ahead of the data, and with these logs, undo log can undo all the incomplete transactions, and redo log can redo uncommitted transactions. This implementation need to write both the log and the data to the persistent memory, brings duplicate write overhead. So since non-volatile memory have slow writes, this overhead will be significant. To reduce the object persistent overhead, UniHeap leverage both atomic update and out of place update. So for small updates, such as those written to a single data field, UniHeap simply use atomic instruction and memory fence. With updates in an atomic region, we propose to use out of place update for performance optimization. We only need to append the update data to the NVM once, so it will reduce the persistent overhead. The log is not needed here because the old data copy is already exists in the non-volatile memory. We now show how we put this optimization into UniHeap system. So as an overview for the system, UniHeap manage the persistent objects in a log structured manner. We store the persistent objects in a shared NVMe heap. enable auto-place update in the data log region, and optimize the latest data lookup with an object index table stored in the DRAM. Let's first look at the NVMe heap. So the heap contains 5 regions. So heap header stores the metadata. Class region store all the class descriptor for different managed runtime. Root table store all the durable root as we discussed before. So object region and the log region store the object data and the metadata. Because we observe that object header is not frequently updated in a transaction, we decouple the object header from its data. So this is because data header could only be changed upon the object allocation or deletion. We store the object header in the object region and object data in the log region. Once a managed runtime allocated a new object from the shared NVMe heap, UniHeap will allocate an object header in the object region. Coming back to the overview, now let's take a closer look at the log region. In order to ensure crash safety and support concurrent access to the objects, we use transaction-based out-of-place update in the log region. We leverage software transaction memory and durable transaction to achieve both mutual exclusion and atomic durability for concurrent object accesses. In the implementation, each transaction can have multiple logs to store the out-of-place update data. Multiple transactions are organized into a linked list. To reduce the storage overhead of the log region, UniHeap garbage collect the stale logs. UniHeap do fast garbage collection to free invalid log periodically and do full GC to free the space if the free space reaches a threshold. The out-of-place update approach can reduce the write traffic to normal memory. However, it also requires an address remapping to retrieve the latest data for the read operation. To do the address remapping efficiently, UniHeap employs a per-object mapping table for address translation. Because each object field has a fixed index value during the object lifetime, UniHeap uses this field index to store the address of the latest update in the log region. The object field index table is cached in a fast DRAM for further performance improvement. With all the above design, we can achieve an efficient and crash-safe persistent object management. Now we look at how we do efficient and correct coordinate GC. As we have mentioned, as a natural requirement for the managed runtime, UniHeap need to support GC for the shared persistent objects. UniHeap used the mark and compact GC to reclaim persistent objects. It contains 4 phases. So in the marking phase, UniHeap set the corresponding bit in the valid bit map to indicate whether the object is live or not. In the relocation phase, UniHeap will allocate new object region and store the new addresses of the alive objects. During the compact phase, the alive objects will be moved into their new addresses. During the cleanup phase, all the old data will be cleaned. So to ensure the data persistency, GC should also be crash safe. So the GC of UniHeap is crash safe by ensuring each GC phases is crash safe. The marking phase is naturally crash safe because it does not change the heap status. As for the relocation compaction phase, we maintain the old object region until the cleanup phase, so we can always roll back before alive objects are moved into the new addresses. Because each runtime have their own GC, we also need to do coordinate GC across many runtime. In this case, we need to make sure that an object is really dead in all the runtime before reclaiming it. UniHeap achieved this property by tracking the object reference and reachability from runtimes. We call this reference as vroot, corresponding to the durable roots, as we discussed previously. UniHeap maintains a mapping set for each runtime to store their vroots. After getting the vroots, we conduct reachability analysis for the vroots and find out all the live objects in different runtime. Then, if an object is not reachable from all the vroots and also not reachable from all the durable root in the root table, which means that it is no longer alive in every runtime and it is also no longer needed to be persistent, it can be reclaimed safely. Now let's discuss how we implement UniHeap. We implement UniHeap system prototype with 9,000 lines of C programming code. UniHeap framework is implemented as a shared library, so including the unified interface and the log structure object sharing algorithm. So during the initialization, each runtime module will dynamically load this shared library and all runtime module could use the UniHeap share library through the unified interface. And the share library talk with the shared NVM heap through direct memory access. This enables fast access to the NVM device that bypass the file system. In our evaluation, we use a 24-core Intel second generation Xeon CPU and a 128GB Intel Optane NVM as testbed. We evaluate UniHeap with a variety of synthetic workloads and benchmarks. For Java, we use VSSV workload over QuickCacheD and H2. For Python, we use Python performance benchmark suite. For JavaScript, we use Jetstream 2, a JavaScript benchmark suite for web applications. So due to the time limit, we only present the most critical results here. We first examine the performance benefit of UniHeap on persistent object sharing. In our micro benchmark, we run one Java and one JavaScript runtime on the UniHeap concurrently. We generate 10K persistent objects sequentially with Java runtime, and then we share these objects with the JavaScript runtime with different managed runtime approaches. As shown in this figure, so both UniHeap and shared memory performs 2 to 3 times faster than Thrift. This is because Thrift has to conduct serialization and deserialization operations. Also, UniHeap performs better than shared memory, so we will explain this with the next experiment. We then examine on real-world benchmarks. We first generate 1 million key-value pairs with Java runtime and store it in the shared NVM heap. And then we run VSSV client as a JavaScript runtime. We use the VSSV-C workload, which is read-only, to issue query request against the key-value store. We compare UniHeap with the shared memory solution and find out that UniHeap performs 21.7% better than shared memory. This is because shared memory do not have data persistent optimizations, such as our log structure persistent object management. So finally, we show the scalability of UniHeap. So we first run the client in one Java runtime and load 1 million key-value pairs. And after that, we increase the number of Java runtime client. And each client will run an individual hotspot JVM. As we show in this figure, for all the workload we evaluate, the throughput will increase consistently as we increase the number of JVM runtime. This demonstrates that the mechanism designed for concurrent data access to persistent objects in UniHeap can scale for multiple managed runtime. So as a conclusion, we present UniHeap, a unified persistent object management on non-volatile memory for different managed runtime. UniHeap provides an efficient and scalable object sharing framework, which significantly outperforms the SOTA object sharing approaches and provide better programmability. Thank you, and I'm happy to take your questions.